Hello and welcome to another Energy Code webinar topic. My name is Mike Barcik and I'm here with and we are going to talk in this one about the topic is commercial envelopes, and right away we're going to see that there's two energy codes that we're addressing, the IECC 2015 and ASHRAE 90.1, and their requirements are similar but they're not identical. So a couple things. A lot of people want to know what Ali and I look like, so I found a picture of us. This one I thought was pretty good. It's got to be on the left. Is that right? I'm not. Anyway, so but we can. I always want to make a plug for where you can find information, and you can get good information from southface.org. On the top, you're going to go to Education, Our Courses, Energy Code, and then Georgia Energy Code, and the resources are there. Including slides, because what we're going to look at is some excerpts from the envelope portion of the full day commercial energy code training. So these slides come out of there and you can get a copy of these. Let's see, I'm going to jump in to sort of the bigger picture here. Is you have to choose which path you want to take, which adventure you prefer to go down. And it can be the IECC route or the ASHRAE 90.1 route. They're certainly comparable. Their scope is very comparable, but their requirements are not always identical. So one may be a little harder here, a little easier here, and you just have to kind of see it for what it is. In general, the main content is envelope, mechanical systems, and lighting. Those are the key elements. We're going, with that, having said that, we're going to go in and just sort of look at a way of thinking about the energy code. You always have to satisfy the mandatory requirements. Those are things like air sealing. There's no trade-off for that. Particularly when you get into the envelope section, you can meet the prescriptive recipe, is what I like to call it, of either one of the two codes, or you can do a fairly simple trade-off, and ComCheck is your friend. ComCheck, we reviewed on how to get that. You basically go to energycodes.gov and you can download that. I'm going to show that really quickly. If I go over here to, that's not it. That's not it. That's some tires. Energycodes.gov, and you can come over here and click on ComCheck. And it'll ask you, do you want the version you can download and use on a desktop, or do you want the web-based version? And that's a good one to use if you're a part of a design team, is the web-based version. And while I'm at it, here's kind of what it looks like, and we may be even demoing it really quickly as we go through. So there's a project screen. You have to pick where in the state of Georgia is this project being located. So I'll say Atlanta, and then you can tell it some basic information about what type of building it is and what size it is. So this is an 8,000 square foot retail building, and once you've chosen that, then you can dive in and do the envelope stuff, and so we'll see that in a minute. Okay, that's slide 25. In terms of complying, you have a choice of complying with the prescriptive code, doing a simple trade-off, or you could always do a much more complicated full-on building simulation where basically within ComCheck, you can do simple trade-offs within the envelope only. Like you can't take credit for more efficient lighting or better HVAC against your envelope. But over here, everything is sort of fair game. So it's a much more sophisticated compliance route, usually requires a professional energy modeler, but it is something that's always available. And I think we'll focus mostly on the prescriptive code and maybe just briefly touch on ComCheck. When you look at ASHRAE 90.1, it basically, and the other code, it essentially says you've got a space that's moderately conditioned, a little bit of heat, a little bit of cooling, it's considered conditioned, or it's essentially connected to a space that's thermally connected. An example of that would be like a spray foamed roof line. You may not be directly supplying conditioned air, into what used to be the attic, but that's effectively inside the envelope. And then ASHRAE has this special column for semi-heated or freeze-protected spaces. So generally, most buildings are considered non-residential. It's most commercial buildings, unless they have people sleeping in it, and that would make it a residential commercial building, like a dorm or a hotel, and then freeze-protected. The other code is very similar, only it's actually a little simpler in the sense of it only has two kinds of buildings. Basically, ones that people sleep in are called Group R, think residential, and everything else is called all other. And that's more or less what defines it. But most commercial buildings are going to need to be meeting the energy code. I always like to remind people, new work needs to meet code. So if you build a brand new building, it needs to be built to code. New portions of existing buildings need to meet code. If you go in and sort of renovate a system, that system needs to be brought up to code. New work needs code. There's also often a list of exceptions. Like if you add low-E storm windows to windows that are already there, you're only making what's there better. You can fix a broken window. And I'm not going to read all these, but in essence, if you just put on a new roof membrane, we're not going to make the code kick in. But if you expose the insulation and the depth of the decking and everything, then that's a good time to bring the roof up to code. So those are kind of, and then like if the code would require a vestibule, they like vestibules, but you're just trying to upgrade the exterior doors, they're not going to make you retrofit a vestibule, so things like that. So we're going to look at the building thermal envelope, and we're going to jump to, I think, well, basically, choose your path. Which one of these do you want to do? ASHRAE is straight across the board. There's no amendments to it. There's a couple of amendments to the 2015. But pick your path, and then you're going to mainly deal in the envelope section with insulation, fenestration, and air leakage. Those are the big three. So I think that's more or less the same thing I just said, and now we're going to dive in. A couple details on insulation. Generally, it needs to be labeled. You want to install it the way the manufacturer says to, which means you don't squish it or compress it, but they understand metal buildings are going to do that. So there's an exception at the purlins for metal buildings. The insulation, this is key, has to be in complete contact with the air barrier. This is really, really critical, and a lot of commercial buildings screw this up. So that's something definitely to pay attention to. Complete, full, continuous air barrier that the insulation is completely in contact with. All right, just some kind of miscellaneous things about, like, if you got a low slope roof or a 3 and 12 or more than a 3 and 12 pitch roof, and it's like a scissor truss, they want you to not use loose fill. Recessed equipment, basically you don't want the can light that's not airtight and IC rated in your insulated ceilings. You need the right one. And any insulation needs to be protected from the elements, especially if it's like running along the rooftop. And then if you have multiple layers, you want to stagger the joints. So we're going to start off with the opaque elements. And let me see if I'm ready to do that. Yeah, I'm just going to jump to this one. So this is, I'm going to mainly focus on climate zone 3. You can see climate zone 3 is the middle of the state, zone 2 is the southern part, and zone 4 is the northern part. We're just going to focus for this on zone 3. You can always download the field guide and you can see all the climate zones. You can see this chart, which comes from ASHRAE. So ASHRAE code says for anytime you have roof insulation, if it's entirely above the deck, it's R25. The reason it's been highlighted here is because that has increased. This is different from what it is in the previous version of the energy code in Georgia. So that's gone up to R25 continuous insulation. It was R20. Metal building insulation has also changed, and attic is staying at R38 in this climate zone. So a couple things to be aware of. You can either do all the insulation above the roof deck and make it R25, or any combination as long as your assembly U factor does not exceed 0.039. So in other words, you're trying to show compliance on either side of this. You can either not exceed this number or equal or not exceed, or you can do at least as good as this or more on this number. And if you can satisfy the left or the right option, you're still considered prescriptive compliance. No trade-off required. So if you can do that for everything, you're done. When it comes to walls, you've got mass walls. Those are usually like tilt-up concrete or block or poured in place concrete, whatever. And that's a 7.6 continuous insulation, or anything with a 0.123 or lower U factor. Metal buildings, we like to joking around and say metal buildings have their own code. They just kind of have to do what they have to do. Metal building roofs having what we call a thermal spacer block at the purlins. Anyway, metal frame buildings, steel frame, this is pretty common, and you'll notice that they want R13 in the cavity plus R5 continuous insulation. So this is new, this is more. And if it's a commercial building that, again, you can either meet the 077 U factor or you can meet the R13 plus R5. If it's a commercial building that has residential occupancy, like a motel or hotel or dorm, then it's even harder. They want more insulation, 7.5. So that's an important one. We want to deal with the issue of thermal bridging and steel studs, and so the best way to do that is with continuous insulation. You'll notice wood frame does not require a thermal break right there. It's only R13. And, oops, sorry. I'm going to go backwards here. I want to walk through a couple other of these numbers here. Below grade walls, that would be considered a basement. So that's no requirement for insulation. A mass floor concrete would be an R10 continuous, and a framed floor assembly would be R30. Heated slabs do require edge insulation, but that's pretty uncommon. That's where you have radiant tubing in the slab. And then the unheated slab is more common. There's no requirement for edge insulation. And then doors, not a whole lot of change there. So everything I just read off are the opaque requirements of assemblies in climate zone 3. And if it's a residential occupancy type building, most of these are the same, but they want a little bit more insulation in the walls. These all tend to be higher. And maybe looks like the same in the floors, and maybe they do want edge insulation in a residential occupancy. I don't think that people are going to do that. I think that there's Georgia amendments on that, but you could also do a trade-off easily. So that is the prescriptive code. In essence, how much R value do I need? And these are all, of course, opaque elements. And there it is for climate zone 2. Still R25. That's a big change right there. And here it is for climate zone 4. Woo! R30 continuous insulation. So ASHRAE has gotten kind of tough on roof insulation. And I think now we're going to jump and see this code. So the IECC, here's climate zone 3, is going to require, actually it looks like R25 is the same requirement, and in R30 in zone 4, so that's consistent. They may have a slightly different formula for what constitutes prescriptive for the metal building or a steel stud, that kind of thing, metal building roofs. But there's also a table like this that has U factors. As long as you satisfy the R value or the U factor, you're good to go. R38, that's pretty consistent. Mass buildings, looks like a little bit more insulation on a metal framed building. Instead of R5, it's 7.5. Oops, I'm sorry. And then wood framing, they want, again, it looks like they want to have a continuous thermal break, so they want foam sheathing. So they're a little more strict on that. No slab insulation. Georgia amended out the requirements for it in zone 4. So if you go to IECC, you don't need slab edge insulation. It's not a big deal to trade that off. It's not a huge impact. Mostly it's about air conditioning buildings in the South. All right, just a couple, let's see, where am I here? I'm gonna make something ring the bell here. So we're on slide 46, and I want to jump down to 50. So jump to there. And I thought I'd show you from roofs kind of a recap. Both codes are very, very stringent about this. We do not want bats on a suspended ceiling tile grid ceiling. So that has been banned in the energy code. ASHRAE banned it 20 years ago, and it's been a good while in the other code too. You still see it a lot, but everybody has seen something like this before, but it does not count as any part of your thermal envelope. You can do it for acoustics. Honestly, I wouldn't do it because I think it makes the insulation gets all airborne and particles floating around, and I just don't think you want it. But you can do it. I would recommend an encapsulated bat if that were the case. But anyway, so not allowed to do bats on a drop ceiling. You are allowed to do this where you have a hard air barrier, and that would be, cruising along this junction right here. You have to have a hard air barrier here, and then blow like in residential style attic, you blow R38 above it. You do have conduction through the trusses, and you do have the danger of someone busting holes up in here, but this is allowed. It can work. It's not necessarily ideal. This might be a good retrofit option for a building that has the bats on the drop ceiling. An existing building, this is something we've done before and help fix problems. So this one is spray foam up against the roof deck, and that's an option, and that tends to stay in place and actually make it pretty airtight. So that works pretty well. Just as a case study, this building, the load dropped from 12 tons to 8 tons when they foamed the roof line and also put in some new light fixtures. So those two things reduced the load by 1/3. So it really did have a big impact. Where's the best place for roof insulation? Continuous above the roof deck. No question about it. It's not broken up. It's airtight. It's got a good track record. And if you your ductwork or air handlers, at least now, is obviously 100% inside. And then if you live in the South, I think it makes sense that you would want that roof to be I was trying to change the color. You'd want the surface up here to be a shiny roof, a reflective roof. And under the old code, it was considered a good idea. Under this code, it's considered basically mandatory. And you have to, in fact, you're penalized if you don't do it. So either you're R25 or you're R33 if you don't do it. So it's really something you want to do. And it has other benefits besides just heat gain into the roof. One of the biggest ones is you usually have mechanical equipment sitting up on the roof. And now the air around the mechanical equipment is much cooler because it's a reflective roof or a low absorption roof. And so that means the heat transfer, you're trying to dump heat at this piece of equipment in the summertime. And if the air on the roof is in the low 100s, that's not so bad. If the air on the roof if that's a dark roof, the air could be 150 degrees or worse. So that's a really significant impact. And it also helps in this thing called the heat island effect. So if you can have a reflective roof, you don't absorb as much. The local ambient temperature stays cooler. There's Atlanta from 1972. Here's Atlanta from 1993. And this is Atlanta in the year 2020. So that's not looking good. Oh my goodness. Okay. All right. So basically, and also they count things like solar PV array. That counts as essentially being reflective roof. Vegetated roofs, those really do work. This is a little tray of a vegetated roof on a fairly light colored gray ballasted roof. But we went up there and that roof was so hot. It was 90 degrees at noon and your face felt like it was on fire. But when you actually looked at the thermal camera, what you see is, hey, that's not so bad. The vegetated roof was a lot cooler. That was 150 and that was 105. So a significant difference. And you can do fancier green roofs, or I am from North Georgia, so this is some of the green roofs that we run into. We don't really recommend those. All right, let's jump on ahead and talk about fenestration. So for fenestration, we've got, again, we're talking about glazing And it's funny because there's a slight difference here. Fenestration in the 90.1 code is basically things that let in light. Fenestration under the I code includes opaque doors. So that's a subtle difference between the two codes. It's kind of interesting. And ASHRAE allows you up to 40% glazing, and you can still be considered prescriptive. The other code only allows you 30%. So there's an example where it's a little bit more restrictive in terms of percent glazing allowed. Again, with ComCheck, you can actually do trade-offs and potentially get a higher percentage of glass because ComCheck lets you trade against the prescriptive. The only other interesting thing is there are certain places where we used to say it was a good idea, but under the new code, it's more or less requiring or prescriptively requiring you to put in daylighting. So this is a big implication, and we'll look at that in a little more detail. So here, really quickly, is a prescriptive or percent glazing rather calculation example. So if you were to do the math, you would do the perimeter around here. You would do 100 and 150. That's 250. Come back around. That's 500 feet around. So 500 feet around times 20 feet. There's 10,000 square feet of gross wall area. Gross wall means it includes windows and doors. So I'll just write that, 10K. And it says right here that you have 3,000 square feet of windows. So that would be 3,000 out of the 10,000, 30% glazing. So you could use either one of the codes for this one. The other big terms that apply are the U factor and the solar heat gain coefficient. And I think I want to jump up at this point. Oops, I may have missed one. Yeah, so prescriptively, here is the code. It is essentially, U factor is pretty easy to hit. These values are not that hard. Most double pane low E will be in good shape easily. And the real challenge is the solar heat gain. It hasn't really changed, but it's always been kind of the tail wagging the dog. We're in air conditioning climate. We really need to focus on low solar gain glazing. And so a solar heat gain coefficient for the glass and the frame of 0.25 or lower is what we're looking for. And then finally, this is new, this idea of the ratio of the visible transmittance of the light, which is what you want, is the visible transmittance divided by the solar heat gain of the window. That number needs to be at least 1.1. So what it's really saying, without saying it, is that some tints aren't going to pass this, prescriptively at least, because it's going to be sort of too dark and block too much visible light for what it does to the solar heat gain. So it's a low E is going to work better than a tint to satisfy that. In essence, this is the chart that gives you credit for overhangs. ASHRAE's chart is very significant. It sort of has 10 different sizes of projection factors. Projection factor is basically the length of the overhang divided by the distance from the bottom of the overhang to the bottom of the glass. So if A is 6 feet and B is 9 feet, the projection factor is 6 over 9, 2/3. So you would multiply any of your glass by 0.56 to give you your effective solar heat gain. So whatever your solar heat gain is, you only have to take 56% of that number, and it almost cuts it in half by that. So you get a lot of credit for projection factors. Here's the other code, the I code. You don't get as much credit. They kind of break up the requirements for what I call small, medium, and large overhangs. Small overhangs, no credit. Medium, a little bit. Large, a little bit more, but not as anywhere near as granular as ASHRAE. And the overhangs need to be permanent. They have to be attached to the building. I mean, these are going to shade the glass, which is great, but they're certainly not permanent. Those could be removed, so that will not count. All right, let's see. I think we're in good shape on that front. Let's take a look. Not keep our beautiful drawing there. Yeah, let's see. daylighting, I guess I'll mention this. Daylighting is something that they're actually trying to sort of encourage us to use either with skylights or windows. They want you to light up half of the floor area in these kind of spaces. The spaces have to be big, over 2,500 square feet. They have to be below a roof with tall ceiling heights. And they have to contain one of these kind of big spaces that usually would be good fits for natural daylight, such as a conference room, convention center, or a warehouse, or a gym, or an atrium, etc. There's always exceptions. I'm not going to go through them. I'll skip all that. This is one that I did want to mention, that the code is big on trying to encourage good sort of passive solar design, where you're trying to minimize the glass on the east and west, and you're trying to maximize the glass on the north and south. You have a much better job, or you get a much better ability to control solar gain if the glass is facing north and south. So this is a picture of the edge of our building right here, and the south face is loaded up with glass. There's exterior shading devices as well as light shelves to help kick natural daylight deep into the space. And these windows are facing east, and you can see they're relatively small. They actually have external shading that looks like a Venetian blind. This particular one is also east facing. It's electrochromic glazing, so it changes its tint throughout the day based on a time clock. And again, I mentioned the visible, transmittance over solar heat gain. So I think that's kind of the big thing there. Let's see if I've missed anything. Oops, nope, I'm gonna back up, sorry. The changing topics, the last topic we want to mention is air sealing of commercial building assemblies, commercial buildings. And I think the codes have it wrong here. They seem to think if you just build out of these materials, it'll be tight. And that's not the case. But that they would like you to build out of something that sort of is an approved air barrier. So in theory, these could all be airtight. I think that's how I would describe it. The places that need to be sealed, they describe how to do it. And they're pretty explicit in this. And a lot has to do with like changes in materials or junctions and things like that. So we'll see that in a second. Most doors are going to pretty much hit that. Vestibules. Vestibules are generally required in climate zones 3 and up. Want them to sort of be like airlock with separation between the doors. They're not supposed to open and close at the same time. And we always recommend you don't condition the vestibule, just make it a buffer space. But a lot of people want to do that, which is unfortunate. Here's a big one. They give you places when you don't have to do it. So not for revolving doors or doors that are not entrance doors or into a dwelling unit. Certainly, they're not required in climate zones 1 and 2. This is a big one, and this is only in ASHRAE. So I'm going to click the highlighter. Oops, let me go back to the highlighter. So in ASHRAE only, if you're building in climate zone 3 and your building is 3 stories or less and your actual building is under 10,000 square feet, you can take an exemption for the vestibule. Otherwise, and that is only in ASHRAE 90.1. The other exceptions are in both codes, but that one's only in 90.1. It's only climate zone 3. So vestibules are becoming much more popular and common in the code. That's just how it rolls. Again, we don't recommend you condition a vestibule. This one was super cooled. It was sweating on the outside. And can lights, we talked about that a little bit. So where is the air going to leak from? Probably from places that are hidden. And it's usually you push the drop ceiling aside and you see big holes in the leak paths. And that's what we want to see that's been sealed. And especially when that space above is used as a plenum, that's a real problem. Okay, so having said that, I'm going to, yeah, it can be a plenum space. So I'm going to jump up here and say, where did we find the leaks were? We blower door tested over 50 commercial buildings, and it was always kind of, oops, it was there. It was at where this block wall meets this corrugated roof. And obviously you don't see that, but that's where it ends up leaking from. And it's just, you've got, you know, this corrugated metal tying into this texture of the block wall, and that needs to be spray foam. That's a huge leak. So that's a big one. So I thought I'd show just a couple other things real quick. This is another common place is when two metal roofs came together and formed a valley. And we love the idea of using continuous insulation above that. But if that assembly is not made more airtight, it will be very leaky. So at the junction of two metal panels, particularly on like a valley, that was pretty bad. So here's examples of trying to fix that. I thought I'd show this one too, which is, again, it's often at a transition. So here we're going from a block wall to a low slope metal roof, and or a low slope roof rather, and you can just see we're pressurizing the building. We're injecting foam here. You can see it cascading down. So that's a fun way to think about that. And then I guess lastly is, again, just kind of thinking about the impact of not doing these details right and what kind of failures do we see besides energy waste, a huge amount of energy waste. Particularly in the South, we have issues with moisture, and that adds to the energy load. There's a lot harder to dry air because of all the humidity that we've let in, but it also causes these kind of moisture damages. So this is the hole. This is often under negative pressure because it's a duct. We suck in humid outside air. It drips on something, and that's the failure that we're looking at. All right, so Ollie, thank you for laughing at my jokes. You really didn't notice that. So anyway, I think that's what we're going to talk about. That was our basic requirements for the envelope.
All right, well, thank you, everyone.
Thanks, everybody.